Okay, so thank you all for being here today. It's my enormous pleasure to introduce you to Hugo Duminil-Copin, who will deliver the Pedro Nunes Lecture. So the Pedro Nunes Lecture is an initiative of SIM, together with the Portuguese Mathematical Society as well, that in the beginning was funded by the Gulbenkian Foundation. And it's in honor of Pedro Nunes, a Portuguese mathematician, whose work I'm advertising in this t-shirt with a dot line. And so let me introduce Hugo properly. Okay, so Hugo Duminil-Copin is a French mathematician, renowned for his outstanding contributions to probability theory and statistical physics, who was awarded the Fields Medal in 2022. He's a professor at the University de Genebra and a permanent professor at the Institut of Hautes Études Scientifiques, IHÉS. Duminil-Copin has made fundamental advances in mathematical understanding of phase transitions and critical phenomena. His work combines techniques from probability, statistical mechanics, combinatorics, and complex analysis. He has been working on dependent population models, whereby the state of an edge is one part of a lattice will affect the state of the edges elsewhere, to shed light of Ising models, which are used to study phase transitions in ferromagnetic materials. Beyond the Fields Medal, his remarkable work has been recognized with numerous awards and honors. These include the European Mathematical Society Prize, the Loeb Prize in Probability, the New Horizons in Mathematics Prize, and the Roald Davidson Prize. He has also been elected to the French Academy of Sciences and is a corresponding member of other distinguished academies. He has been awarded an ERC grant, has served as editor of several leading journals, and delivered talks in many highly reputed institutions worldwide. So please, the floor is yours.
Well, thank you very much. Thank you for coming. Thank you for the very kind introduction and the invitation. I'm very happy to be here today to present a little bit of my field of research. And I decided to do it by going through one kind of archetypical example of what we call a lattice model. So it's called the Ising model, the example I chose. And through this example, I want to give you a little bit a glimpse at what we do in statistical physics. So let's start by the beginning, by defining the model, so definition. And here, maybe I don't want to be throwing at you the definition too brutally, so I want to tell you how we cook it up. And the first idea is that we start from an experiment that I'm not going to do because I discovered that apparently universities don't like that you light things up in the middle of their buildings. Of course, the physicists are allowed to do it, but apparently we are not. So imagine, we are going to make what mathematicians do. We are going to use our imagination. Imagine that we have a magnet that is sticking to your fridge or something like that, and that you start heating it up with a light. Okay? Something that you probably never did, and that I would not recommend. But if you try to do that, something funny happens. It's kind of an experiment you can try, is that at a certain temperature, the magnet is going to fall. Why? Because in real-life magnets, the temperature is impacting the strength of the magnet. And it's so much impacting it that when you increase the temperature, when you reach a certain temperature, let's call it Tc, it's the temperature of, it's called Curie temperature, but here for us, C will be critical. At this critical temperature, the magnet stops to be a magnet. Okay, so here you are a magnet, and then above you are what we call a paramagnet, which is something that is not spontaneously magnetized. Okay? And the question is, can we mathematically try to understand why the temperature has an impact on the magnetic properties of a material? Okay? So this is how you sell to get a grant. Then, of course, after you define the model and you do math, but at the beginning, that's how you. So how do we cook up a model for that? if there are physicists in the room, I totally apologize. I'm simplifying things. I'm going to think that the Ising model is a good model for magnetism. I very much know that it's not the case. Don't shoot at me, please. But for this talk, it will be good. So good enough. So let's try to cook up this model. And first thing we are going to do is we are going to try to make a definition of what is a magnet from the mathematician point of view. So what we are going to imagine is that a magnet is in fact a huge collection of small magnets. We call them spin just to avoid confusing the two. So it's like in my magnet there are tiny small magnets. In fact, these are usually the role is played by the electrons in atoms, but let's not really care about that. So you have tons of small magnets like that. Okay? And I'm going to make a few assumptions on these magnets, these spins. The first assumption, first hypothesis, let's call it H1. So H1 is going to be that these small spins, they are regularly spaced. Already it's a little bit of something not so clear, right? In fact, the regularly space allows us to have translation invariance and many things that mathematicians like. And in full honesty, you can get rid of that if you really want in many contexts. But so we are going to think that the position are on a lattice. And since I'm not so good at drawing things, I'm going to take ZD, a grid. Okay? Here I draw Z2, but you can think of Z3, we will, for instance, or Z4, etc. Second assumption, and this one is actually a little bit more problematic, even way more problematic, is that we are going to assume that these small spins, these small magnets, they can point in two opposite directions only, north or south, or as we say in math, plus or minus. Okay? So the sigma x are going to be valued in plus minus 1. Okay? So the position x are on a lattice, and the sigma x are exactly encoding the orientation of each spin. So a magnet sigma, for me, it's going to just be a collection, a function, if you want, of the vertices of a lattice, or maybe a finite piece of the lattice, into plus minus 1. That's a mathematical magnet. Okay? Once you have done that, so this was the definition, it was step 1 in some sense. You get to step 2, and step 2 is typical from what a physicist would do and a mathematician would do, is that these magnets, they are a huge collection of spins. The big magnet is a huge collection of spins. It's very complicated to keep track of everything. The temperature is having an impact. It's kind of acting like a disorder parameter. Everything is very complicated. So what we are going to do is that we are going to simplify things. And there is one way of simplifying things in math which is drastic. It's actually in many other fields of mathematics, it's too drastic, is to pick something at random. Right? We are going to look at the typical behavior. If you think about it, many mathematical subjects are actually focusing on atypical things. If you take certain curves at random, you get something actually not so interesting, and the math becomes interesting when you look at atypical things. But here, in this case, we are lucky enough. The typical thing is what we see in nature, so we can take things at random. So we are going to introduce randomness as a simplification thing. So in order to introduce randomness in physics, usually you need to know what is the energy of your system. So what is the energy of a magnet? Let's call it H of sigma, like H for energy. H for Hamiltonian, but so how do I measure the energy of a magnet? Well, the small spins, I told you before, I think of them as small magnets. What do magnets like to do? They like to align. So I would like to say that if I zoom in and I look, I don't know, here at this pair of neighboring, so here there are two small magnets, right? let's say this and this. I want to say that the energy between these two spins is going to be higher if they disagree than if they agree. And there is a natural thing. If this is position x and y, I can say that the energy is minus sigma x sigma y, which is plus 1 if they disagree and minus 1 if they agree. And what I do if I want the total strength, I just sum over every x and y which are neighbors. Let me denote it like that. Okay? So here, you may think, oh, that's a little bit strange because, I mean, this magnet probably also interact with this one and this one and this one, etc. But here I'm going to do a kind of an assumption that the strength is mostly due to the nearest neighbor interaction. Where is the guy that is the closest to you? Okay? I mean, the guys, because there are 4, I mean, 2D in general. You can actually relax this. It's not a very big assumption, but for this talk, it's going to be good enough. Okay, so this is the energy of my magnet, and then I trust Boltzmann, and Boltzmann tells me where the probability of a certain magnet then becomes proportional to exponential of minus the energy. So the higher the energy, the smaller the probability. And how much you care about the energy is actually related to the temperature. The temperature is telling you how much you care. So there is a temperature parameter, T like temperature for once, that I introduce like that. And here for probabilists in the room not to run at me and try to kill me, I'm going to renormalize that it's a probability measure. Okay? So this is the way of sampling at random. The probability of a certain magnet is given by this. Okay? Okay. If you have a probability measure, what you can do now is try to measure something. Right? This is why you introduce a probability measure. So what do we want to measure? So once we have a magnet, there is a natural quantity that you could try to look at. Let's call it m of sigma, which would be the strength of the magnet. And what can I measure? I mean, how can I measure it? Maybe I can just say I look at the average of all the spins. If this is very close to 1, means that basically everybody is pointing north, which is kind of saying that they will collectively attract things quite strongly. If, on the other hand, you know, half of them are pointing in one direction, half of them are pointing in the other direction, then they kind of cancel their attractive strength, and the magnet basically gets a zero magnetization, so a strength which is 0. Okay? So this is for each individual magnet, each possible realization of the magnet. So now that I have a measure, I can introduce the average magnetization to be just the average of the magnetization for each realization. And at this stage, you know, I mean, I'm always trying to answer questions asked by the speakers, and I never manage. But this one, I think some of you will manage. What is m of t in my case? To what is m of t equal? Sorry? The people who saw the talk yesterday are not allowed to answer. You know, you are not going to brag easily today in front of all your colleagues. That's not going to work. So you get 0, right? Why do you get 0? Because this definition is made in such a way that if you flip all the spins, it doesn't change the energy. If it doesn't change the energy, it means that sigma and minus sigma exactly have the same probability. But of course, the magnetization of minus sigma is minus the magnetization of sigma. So this symmetry gives you that this is always 0. Okay? So careful, or I don't know, m of t equals 0. not so great, right? I mean, at least a little bit boring, and also, at first sight, it looks like there are no magnets. But here, the thing is a little bit twisted, like this symmetry is not taking into account that usually a magnet doesn't exist just in the void. It's not alone in the universe. A magnet is actually in a magnetic field. So you may want to be breaking the symmetry by introducing the existence of a magnetic field. And for physicists in the room, I'm going to do it in the wrong way. I know this is not the right way, but it's the simplest way for mathematical talk, and it's equivalent to the right way. So the right way for introducing randomness, magnetic field, would be to, this is here, to add minus h sum over x of sigma x. You see, imagine h is the strength of your magnetic field, and it's saying, for instance, if it's positive, it's favoring that spins are positive. That would be the right way, but this is not the way I'm going to do it. I'm going to do it in a, or maybe I do it like that because I was told there are physicists in the room, so I should be careful. I'll try to be careful. I will. Let's do it that way. Who cares? I mean, at the end, who cares? So this is, and like that, it's a novel talk. From there on, I don't know how it's going to go. I'm sorry for what will happen. Okay, so you agree now it depends also on the parameter h. And you can look, if this was t, you can look at what happens when you add this h. And here, a priori, what will happen? H is kind of favoring pluses against minuses. And in fact, the temperature is just telling you how much, but I mean, at the end, it's always favored. So in this case, you are going to get something like that at every temperature. So again, a little bit boring. Before we had always 0. Now we have always strictly positive. But it's because we didn't do the last step of the construction of a statistical physics model, is that our magnet is a huge collection of spins, and huge for mathematician means only one thing, it means infinite. So what we are going to do is take the infinite limit. Here, I was a little bit careful to sweep that under the carpet, but here it depends on V, on the set, right? And in order to define this, I definitely want V to be finite. I don't like infinite sums of plus and minuses. Okay. But nothing prevents me, by the way, this was also depending on T and H, nothing prevents me from taking the limit when V goes to infinity. So if here I defined mv like that, what I can do is take m of th to be the limit when v tends to zd of mv th. Think of v as being bigger and bigger boxes. I mean, in fact, it doesn't depend on the way you do it, but let's ignore this difficulty. It's not entirely clear that there is a limit here, but there is one. Okay, trust me, this is the kind of things you don't want to know, how you do that. And once you have that, well, this is strictly positive still. You didn't fix the problem. But your goal is to know what happens. I mean, if you put basically any material that is, like when I said here there is a phase transition, if your magnet, even at very high temperature, is in a magnetic field, it will get a magnetization. The important thing is when you remove the field, then you should lose it. So the interesting thing here is, in fact, to look at what happens when you remove h. So what happens when you take h to 0, let's say from, okay, here it was h positive always. You could take edge negative, but I mean, I don't like negative numbers because they make me make mistakes. I like them, don't tell them, but less than the positive ones. Okay, so now you have a quantity, which is the limit. So here, by the way, this limit is very intuitive, because in fact, when h goes to decreases, you expect this magnetization to decrease. So in fact, it's really just decreases. It's always strictly positive, it decreases, but then it can get to 0 or to a strictly positive value. So this m star of t can be 0, or it could be non-zero. You don't know. And in fact, if I go back to this picture, the dichotomy is going to be, do I have m star of t strictly positive, or do I have m star of t equals 0? And these are the two possible behaviors. And my goal is to see whether in this model, which is now basically well defined up to a few details that are swept under the carpet, for this model, do I have a transition between values of t where it's strictly positive and values of t where it's 0? Okay? Very good. You have no choice. I'm saying that, but this is a rhetorical question. I will keep going anyway. Okay. So, you survived the first part of the talk. Congratulations. Second part of the talk is to say, okay, so can we prove that there is a phase transition? So is there a phase transition, meaning a change of behavior between strictly positive magnetization, spontaneous magnetization, or zero spontaneous magnetization? And this is the place where I can start telling you a little bit of the history of the things. And the history started 100 years ago. The Ising model was introduced by no. No, that's a tradition that we have between physicists and mathematicians. We do not name the problems after the people who invent it. That would be too easy. So it was introduced by Lenz, who was Ising PhD advisor. And it was introduced in 1920. And in 1925, Ising, so at least he still did something on the model. What he did is that he proved that Tc of z, because you agree the base graph probably impacts things. So Tc, by the way, is the supremum of the values for which is strictly positive. Right? It's perfectly defined. So sup of the t such that m star of t is strictly positive. And Ising proved that if you look at it on z, so in one dimension, you look at a one-dimension chain, it's 0. And this is a little bit problematic, because that's not what we would like, right? We would like this thing to be neither 0 nor infinity to prove that there is a change of behavior, right? Okay. Worse than that, Ising tried to, I mean, of course, he pretty much knew, right, that magnets are not one-dimensional. So what he did is that he tried to mimic a three-dimensional thing by using exactly what he could do. So he tried to patch kind of two-dimensional things again, I mean, along one line of a one-dimensional line. And for this thing that looked much more three-dimensional, he also found that Tc is 0. So what he did is that he conjectured that Tc is always 0. And that was very bad, because in 3D, it was saying, well, no phase transition. So the Ising model is a terrible model for ferromagnetism. He found that. It was a little bit disappointing, according to him. So the little bit disappointing was that, I mean, he stopped academia. He left academia. And for 20 years, he didn't know that his name became one of the most famous names in physics, thanks to this paper and its prediction. But the prediction was a very bad thing, right? I mean, it was very bad news for the model. Second bad news for the model, Heisenberg, the famous quantum physicist, introduced another model for the thing in 29 or 28, 29, whatever. And he introduced a model which has the advantage of being quantum. Because at the time, it became pretty clear that ferromagnetism is related to the quantum behavior of electrons. It's the magnetic moment of electrons. It's something that does not appear classically. And the problem is that the Ising model, in the way it's cooked up, there is no quantum physics in it, at least at this stage. So you are trying to explain something using just the wrong physics, which usually is not the right thing to do, at least when physicists are in the room. For mathematicians, if they leave, you can do it, it's fine. We will still publish the papers. But, OK, so what were the pros? Because, I mean, if I'm talking today in front of you, is that probably people kept working on the Ising model. I'm not the only one that took the ball back 100 years later. So the pros, they are subtle, but they are, in some sense, very interesting, I think. So, I mean, the first one is not that subtle. So the first one is due to Peirce in 1936. And Peirce proved that Ising is totally wrong. So this is a trivial result. So not only it was a trivial result, but the prediction was totally wrong. So this is, as I usually say, the message of hope for PhD students in the room. You can become very, very famous, even with a trivial PhD. You just have to do a wrong prediction attached to it. I would not necessarily recommend it as a career advice, but well, maybe I just did it. But anyway, it's always strictly positive. In fact, Ising was fooled by the fact that his three-dimensional system was, in fact, really a one-dimensional one. He just didn't realize it. In fact, today we even have ways of looking at the Ising model on very exotic graphs and graphs that have dimension which is not an integer. And really the prediction is that even if the dimension is 1.00001, it will strictly be positive. So it's really only for linear chains. So that's the first observation of Peirce. And the second observation is maybe more important. So this at least tells you that in dimension 3, there is a phase transition. Good. But it doesn't totally fix the fact that the model is still not quantum. And this will not be fixed, just that you know. But Peirce did notice something interesting. It is that other phenomena were studied at the time. In particular, people were interested in collective phenomena, like collaborative phenomena. And they were also interested in binary alloys, so mixture of two elements, like two molecules or two. And what happens is that in these two other cases, they cooked up models that were, in fact, exactly the Ising model. It was not plus minus 1. It was molecule A and molecule B, but it was exactly the same models. So here, it illustrates something that I like to remind people, and in particular, this is something that physicists teach us very, very efficiently, is that there is a trade-off when you do science in general, but math or physics in particular, is that when you try to look and this is not math, it's just meta, but if you look at the precision of your model, there is a trade-off. In the sense that the more precise your model, the more accurately you can predict one phenomenon in particular, something. So here we have a physicist in one lab. He is doing his experiment. If you do a model which is very precise, you may be here, describing well. But there may be another physicist here, doing another experiment. And maybe a precise model will be like that. But there is actual interest in having less precise models. Because what happens with less precise model, of course it's frustrating because it's going to be less precise. That's the definition of the word. But the less precise model may be here, in the sense that it may actually treat in a similar fashion many different phenomena that you see in labs. And to illustrate that, for instance, concretely, the Ising model was one of the models that helped people understanding the concept of universality. The fact that many systems do behave the same even if they have some features that are different, apparently. It's sometimes core common features that rule the behavior of the system. And the Ising model was extremely good at that, in particular by showing that certain things were not changing when you are changing the lattice, etc., etc. So it may be very interesting to have fairly rough models for a wide variety of phenomena, and the Ising model is the archetypical example of that. So Peirce kind of saved a little bit the Ising model by making this observation that it was actually modeling different phenomena. But the person that I think really gave the Ising model its noble place in mathematics is Onsager, Lars Onsager, in 1944. Or 42, 44. So, you know, at the time, people liked to make pranks. I don't know if it was a prank. But so in 42, he showed the formula, then didn't explain how you prove it, left people unaware of the proof for 2 years, and then decided that he will show the proof to the world. So this is why 42, 44. In full honesty, 44 is the first time we saw a proof of that, but it was absolutely horrible. So Kaufmann, a few years later, she was a student. Maybe there is 12. I'm always confused. Okay. Add it if you wish. There is probability 1/2 that it's there. Breuer, Kaufmann reprove this result in a much better. I'm going to tell you what is the result. Don't worry. I'm going to go back to 42. In 48, with Lars Onsager, she provided an even better proof. And since then, there have been a number of proofs, many, many proofs involving algebra, analysis, combinatorics, blah, blah, blah. And there is even a paper that is called the 399th proof of Onsager result. There are not 399 proofs. The people who was from Marseille, as we say in France. But he was exaggerating a little bit. But still there are at least like a 10 or 15 proof of this result. So what the result says exactly is not so much mattering. I'm going to explain to you one of the corollary, like one of the improvement. Let's say it's not just a corollary, but improvement of the result, which is going to be much more in line with what I described. So Young, in 52, based on these ideas of Onsager and so on, he proved that on Z2, you can actually compute the spontaneous magnetization explicitly. And it's equal to 1 minus 1 over hyperbolic sine of 2 over t to the power 4 to the power 1 over 8. And you take the positive part of this. So this is the kind of things you should not tell somebody in a bar, right? Except if you want to empty the space and have room to sit. So this is typically the kind of things that scare people that don't do math or physics. But anyway, sorry. So he computed that, and Young is somebody you probably already heard about, because this is a Young from Lee Young, Young-Mills, Young-Baxter. It's the same person. It's one of the most influential theoretical physicists. He was, okay, every single time I try to avoid this joke, but I don't manage to. He was very young at the time. I'm really sorry. he was in his youth. Okay, let's put it like that. And he described actually this computation as one of the hardest computation he made in his life, which when you see the breadth of the physics that he produced is saying something. So it's not an easy result, but we have it. And when you see that, because there is a plus here, it's actually very easy to compute TC. TC is 2 over log 1 plus square root 2. But, I mean, it was not easy to the point where I was expecting you to do the computation by head, but this is what you get. So very good on Z2. Not only it's strictly positive, but it's exact. And you have a pretty precise behavior here, right? I mean, if I plug this function, I have something pretty cool happening, right? Because it's starting at 1, of course. This is the max of what you can get. At 0, you have only one potential magnet. And it gets like that, reach 0, and stay at 0 at TC. And here's the behavior. If you look at this, it's in TC minus T to the power 1 over 8, which is kind of maybe not that intuitive, right? So this is one of the interests of this whole body of work, and this was one of the first time people were getting what we call non-mean field exponents. So in physics, very often, to simplify things, and it's a very powerful technique, you kind of try to forget the geometry on which you are working. In particular, here, you try to forget the Euclidean distance. You just say every spin interacts with everybody. And when you do that, you can actually prove that there is a critical temperature, that everything works. But you will get a behavior of the magnetization as Tc minus T to the 1/2. Not 1 over 8. So this was one of the first time that physicists and mathematicians were able to compute rigorously a non-mean field exponent. And this is one of the reasons why this is one of the major achievements of this theoretical physics. And so you see this is mostly theoretical physics at this point, but things are rigorous. So we just take it as mathematics. You know, physicists are mathematicians when it's good for us. I'm encouraging the thing in the other direction. We also want to be called physicists once in a while. But here it's clearly the case that they can be considered as rigorous theorems, and it's one of the main achievements of this period. Okay, very good. So it seems like we are on good track. We are in 42. I have 3 hours, right? Just to check. Well, if I want to get my plane, maybe not 3. But so what's the next step? Well, it looks great. You can compute things explicitly. The problem is that in order to do this, you rely on a very, very peculiar property of 2 dimensions in this case, which is that the Ising model in 2 dimensions is what we call integrable. It's a kind of classical version of integrability in quantum physics. So in particular, so careful, slippery road, integrability is used here. And basically, integrability, if you take also the mathematical definition, just means you can compute everything. The thing is so well determined that you can compute things. But the problem is that I told you, well, I'm making this assumption. I mean, of course, I'm allowed to lie to you, or at least I took the liberty of lying to you. And I said, oh, don't worry, nearest neighbor, it's nothing. The guy interacts just with the neighbor. But I mean, this is an assumption that you definitely would like to relax. I mean, if your model depends totally on that, it's going to be problematic because the real-life magnets definitely don't have a notion of best 4 friends or 2D friends, and I interact only with my friends and not the others, right? So for instance, you may think, okay, I would like also to interact with next to nearest neighbors, maybe with a much weaker strength. So it's not going to be plus minus 1, but plus minus epsilon. But I definitely want to take this into account. Well, whatever the epsilon, you lose this. Your ability to exactly compute things completely breaks down, because this integrability is related to algebraic properties of your Hamiltonian and so on, and just they are very sensitive to the geometry. As long as you are planar, no problem, you are the king or the queen of the world. But as soon as you introduce non-planarity, it breaks down. So this is not the end of the story. By the way, when I mentioned universality, because you can compute things here, what people did at the time is that they said, okay, you know, you like the square lattice, but I don't like it. I prefer the hexagonal lattice. I cannot disagree with that. I love the I love the hexagonal lattice, except when I have to draw it. That's the only time. I also love administrative stuff, except when I have to do it. So hexagonal lattice, you can try to compute things, and you will not get 2 over log 1 plus square root 2. You get, I don't remember, but maybe 2 over log square root 3. But you can do things explicitly. And the interesting thing is that you get to another point. OK, I realize I'm regretting what I just did. OK, forgot square root 3. I don't want to place it with respect to 1 plus square root 2. So somewhere there is hexagonal 1. And what you see is that it has a different TC, but the behavior is again TC minus T to the 1 over 8. And if you take the triangular lattice, you get another value, but you get again TC minus T to the 1 over 8. And this is typically what I mentioned by universality. It's typically something that people realize there. They also use Monte Carlo things and so on, but they had a proof that the critical exponents, what we call the behavior near the critical point, are universal. You will tell me, yeah, but I mean the critical temperature isn't, right? But that's what you see in real life magnets. If you take a magnet made of iron, its critical temperature is above 700 degrees. So you cannot, it's 782, something like that. So you cannot just use a light to I mean, you are going to burn your fridge. Just that you know. Just to be clear, I will not pay for the fridge afterward. But if you take some alloys, and this is actually the experiment I usually do when I'm allowed to do it, you can, with a light, I mean, they have like a temperature, a critical temperature of around 300 and something, and then with a light, you manage to reach the thing. So the dependence of the critical temperature on the structure, the microscopic structure of your material, this is totally fine. What is interesting is this universal behavior near the critical point. This was just a parenthesis, but anyway. OK, but here we are still in 2D, right? Actually, really in 2D in the sense that if you break this and you look at this next to nearest interaction, you are back to ground zero. And your problem is that what about 3D? I mean, my magnets are in 3 dimensions. So there, it's not integrable, and I will not recommend to try to prove it's integrable. Maybe it is, but I would definitely say that this will be disappointing. So we do not really expect the Ising model to be integrable in 3D. But we know that TC is strictly positive. So there is a phase transition. So what is the kind of question we can ask if it's not trying to compute the critical parameter? So of course, if you cannot compute TC, if it's not integrable enough to compute TC, you cannot also get an exact formula for this. This would be completely crazy to try. But what you can do is you can try to ask, is the phase transition what we call continuous? Because when you look at the experiment of Curie, let's say now this is Curie experiment with 3-dimensional magnets. He used like different magnets, and for all of them, he measures the magnetization as a function of the temperature. Hello. And if you do that, you realize that the magnetization behaves in a continuous fashion. It is not doing this, which was a priori a possibility. it's not doing like that. This is called a continuous phase transition in opposition to discontinuous phase transition. And phase transition that are discontinuous, you actually know two of them with the same material. It's water. When you bring water to 100 degrees, it becomes vapor, and just the volume of the vapor taken by the same water, H2O, becomes 10,000 times bigger. That's actually the principle of motor based on vapor. If you bring, another way, which is maybe a little bit less dangerous for your kid if you want to do the experiment, or your friends, is if you cool down water, you put it in a freezer, you really put water up to the top of your bottle, the bottle is going to explode. And kids love things that explode, especially. And this is because, in fact, when you cross 0 degrees, water has a jump of the 10% or 20, don't get me on this, but there is a difference in volume per unit of mass. So these are two discontinuous phase transitions, but in the case of magnetization, we expect continuous. So question, can we prove it? And so I want to finish the talk. It's not... How long do I have? Tell me that.
10 minutes.
Whoa! At least. I heard at least. Yes. Very good, very good. So theorem, myself, Sidoravicius, and Eisenman. And I want to tell you a little bit about the proof, but the theorem is saying m star of t is continuous in 3D. So the phase transition is continuous. So despite the fact that we cannot compute TC, despite the fact that we cannot, it's even harder, compute the spontaneous magnetization, we can still prove that the phase transition is continuous. And this is good because this is the beginning of the story usually. Once you have a continuous phase transition, in particular the behavior at the critical point is actually marvelous. There are what we call emergent symmetries. So you can prove conformal symmetry or things like that. You can try to compute the critical exponents, etc., etc. There are tons of things that you can do. Okay, so let me try in 10 minutes at least to tell you a little bit about the proof, because I think it exemplifies something that is quite interesting in statistical physics. And in order to do it, the first thing I'm going to do, so let's start the proof. I do not guarantee that you will be smiling at the end, but anyway. So to start, let me tell you that in order to do that, you need to prove m star of t c equals 0. That's actually the difficulty. Otherwise, you would actually be in this context, which is... so you need to prove that at Tc you cannot have spontaneous magnetization. It's 0. And in order to do that, there is a way of measuring it, which is to try to look at Tc, at the correlation between 2 points. So how much the two spins, how much they interact with each other. If I tell you this is plus, how much it twisted sigma x to be plus. When x and 0 are farther and farther away. And it's pretty natural to expect something is that if you send one point to infinity, the two spins probably are farther and farther away from each other, so they are going to act in a more and more independent fashion, right? So this should be mu Tc plus of sigma 0 times mu Tc plus of sigma x. By the way, by translation invariance, these are the same. But also by translation invariance, this can be rephrased easily because the spontaneous magnetization was the average in space. But if there is translation invariance, it's actually exactly going to be the average of 1 point. So this is, in fact, m star of TC squared, because there are two people. Good. Good because actually, and by the way, this is true at any t, but I'm using it at TC. There is another thing that is true at TC, is that for the measure when I don't break the symmetry, when I don't put the plus, in fact, this measure is kind of continuous from the right. I don't explain exactly why, but it's actually true. It's yes, that's I have only 10 minutes, so blame him. So this continues from the right, but from the right, you are in the area where you have disorder. Things tend to 0. I mean, they just the spins have 0 average. It tends to 0. So this limit is 0. So it looks like we are going to be happy soon. M star of TC equals 0, right? Voila. Yeah, that was not. Yeah. To be honest, it's almost what I believed the first time. I was like, oh, it's very easy. Because, of course, no, I'm not, I mean, I have glasses, but I can see what I write. And, of course, there is a difference between the two, because here there is a plus and here there is nothing. So that I saw it the first time, but I thought it's very easy. I just have to prove that the two things are equal. I just have to relate this kind of quantity to this one. And I thought, oh, this is a big step, like I really progressed, because it's not totally trivial to prove that. So I thought, okay, after having done that, it's trivial to conclude. Except that discontinuous phase transition, which is what I'm trying to fight, right? Discontinuous phase transition are exactly transition where at the point of the transition, there are different states of matter. Think of water. You cool water at 0 degrees, there is going to be coexistence of water and ice because both things are legit state of matter at 0 degrees for water. Well, these kinds of describe the different state of matter. So proving that they are equal is actually exactly proving that you have a continuous phase transition. I mean, at the end, you rephrase the thing, but it's the same difficulty. So you are back at this stage. I may be a little bit happier, but so how do we prove that they're equal? So that's why I will take the 5 last minute. Yeah.
At least.
Aha! I like this guy. So, how do you prove that these things are equal? That's where you reach half of my talk. I mean, in full honesty, in France, usually I say, oh, it's the true normand. You know, it's what you eat at the middle of your dinner to be able to restart a second dinner just after. So it's like very strong alcohol. It dilutes everything you ate, and you can. So this is half talk. So let's do the true normand. So the true normand is going to consist in completely ignoring everything you learn up to now. This is usually easy. And think of a totally different phenomenon, which would be trying to understand a porous medium. Yes, people like, oh man, this is too much physics. So you try to understand if water can flow through a medium. And what you can do is you can imagine your medium as kind of a random labyrinth or a random graph made of edges again. And you think that some of these edges are porous to water because there is nothing there, for instance. And some aren't. So, I mean, okay, now I remember why I drew in red the water last time. So some edges are porous to water, some are not, okay? And you can decide, for instance, at random, which edges, because you are not going to go into your material to see what happens. So an edge is going to be red with probability p, and gray and white with probability 1 minus p, okay? And you do it independently for all the edges. So the state of edges are totally independent. And what you look at after you did that, so you sample a random subgraph of the original graph, and you look at the connectivity properties of this graph. In particular, you can look at them depending on the value of the parameter p that I just mentioned. And if you take p, which is 0.499, what you end up in a big box is tons of small connected components. They are actually logarithmic. But if you do the same at p equals 0.501, what you end up with is a very different picture. You have a huge connected component, and inside some small holes with like a tiny connected component in it. But you have a huge connected component going everywhere. So this model is undergoing a phase transition at 0.5 between a phase where all the connected components are small and a phase where you have a huge infinite connected component and tiny, small, finite connected components. So why do I tell you that? This is called Bernoulli percolation, by the way. Now we forget about the true normal and we go back to the proof. You are already very happy. Because what happens is that these quantities, for instance this one, so the correlation in my system, it can be rewritten as a connectivity probability in a certain percolation model. So there is a way to sample subgraph of ZD in such a way, so let's call P the measure that is sampling the thing, such that the correlation between sigma 0 and sigma x are exactly the probability that the 2 points are connected by a path of red edges. The way you sample this is not this one. It's way more complicated. Like the state of red edges depend on each other. That's what you referred to in the introduction. So it's a very complicated dependent percolation model. But it offers a dictionary between the Ising model on one side, remember explaining magnetism, and a percolation model which seems more suitable for porosity of materials. So two different worlds link by this connection. And this link is actually pretty strong because you can take mu plus Tc and try to use the same kind of dictionary that allows you to do that. I will not explain how you pass from this to this, but there is a technique. And if you apply the same technique, you actually get this. And I'm really, really very close to completion, don't worry. You get that the difference between the two quantities is actually given by the probability that both points are connected to infinity, are in a connected component going to infinity. But now, here is the good news. The good news is that the picture is still on the board. Here, I told you that in Bernoulli percolation at least, when you are in the phase where you have an infinite connected component, there is a huge infinite connected component, and all the finite ones are tiny. In fact, this infinite connected component is unique. Really, it's a huge one, and it's unique. And it's something very robust. It's very difficult to cook up percolation models that have several infinite connected components. Usually, when there is one, it's so big that it takes all the space. So here, if 0 and x are connected to infinity, what do I deduce? I deduce that they are connected together because they are in the same connected component. But if they are connected together, this quantity is necessarily smaller than this. So this is smaller than twice mu Tc of sigma 0, sigma x. Well, that's good. This goes to 0. This goes to spontaneous magnetization squared. This is what we proved before. This is what was there. So the spontaneous magnetization is equal to 0. In fact, this is actually equal to 0. There is no infinite connected component. So in fact, you really have equality between the two, but you don't even need that. So this is the end of the proof. And really what has to be remembered from this proof is that by rephrasing the model in a different fashion, in particular here by using what we call a graphical representation, you translate a problem that is extremely difficult on the side of Ising into a problem which in full honesty is not that difficult on the percolation side. And of course, it can go both ways. Sometimes the problem in percolation gets rephrased into a spin system, which is much simpler to study. So you have dictionaries like that between different statistical physics models. And these are dictionaries that will be hard to discover in a lab, right? Because you will be actually talking to physicists with very different specialties. By the way, I did not invent this connection. This connection dates back to the 70s. But what happened, and this is, I will finish on this, these two sentences. I mean, it will be maybe three, but it's already maybe three. Okay. Oops, I'm going to get caught into a recursive loop. But basically, when I arrived as a PhD student, the understanding of Bernoulli percolation was already extremely advanced. It dates back, it was introduced in the 50s. And using independence of the state of edges, you can do many things. But as soon as you introduce dependency between the different edges, then most, if not all, basically, the theory was collapsing. Like really a lot of the theory was collapsing. And so one of the things I tried to do when I was younger, and I still try to do, is to cook up a theory of percolation models which have dependency. Because we know for a very long time that you can rephrase many statistical physics models into percolation models, but they have dependence typically. They are not this model. And it worked very well. It happened that for many models with dependency, we did manage to develop a very advanced theory of these percolation models. And in particular, this is an example of we translated to a percolation model that was dependent, but now we have a good understanding of this dependent percolation model, and we could deduce, for instance, that there is a unique infinite connected component, etc., and therefore conclude the proof. Thank you very much for your attention.
Thank you. Are there any questions? Please, Phil.
Thank you very much for this very beautiful lecture. I'm one of those annoying physicists.
No, I love you guys.
That's not in your list. But often physicists are more interested, well, at least the type of physicist I am, in 4 dimensions. So there are some models you can build in 4 dimensions that resemble, in a sense, Ising models. So is there any results? And obviously we are interested if these models have phase transition. Examples of these are, for instance, Higgs model and all the implications.
I like this model as well.
And so on and so on. Are there results in this direction?
Okay, so I'm also the kind of mathematician that like 4D, so we are going to be good friends. Yeah, I mean, let me first go in your direction and then tell you where I stop, in some sense. So you can look at the Ising model in 4D. There is no problem with that. And actually, you could think this is totally unnatural because magnets are in 3D. But again, remember that it's actually not such a good model for magnetism. If you do in 4D, the advantage is that you are in Minkowski space. You are 3 space dimension, 1 time dimension. And in fact, there is a way to relate the large-scale behavior of the Ising model at criticality in 4D, so when you really look at it at TC, and quantum field theory. So it's a way, at some point it was even expected, even though pretty quickly physicists understood that this would not be very useful, but it was expected that by taking the scaling limit, so the large-scale behavior of the Ising model in 4D, you could maybe construct a quantum field theory, which is what we call non-trivial, which means that would describe particles that interact with each other. So pretty quickly, physicists noticed that it looked like this Ising, or the phi-4 model, which is related to it, would actually lead to what we call a trivial quantum field theory, which would be particles not interacting with each other. But it was an actual mathematical challenge to prove that. It took 40 years, basically. So Michael Eisenman proved the result in 5D and more, which was not the dimension that was interesting from the point of view of physics. Actually, Fröhlich also proved it independently. And with Michael Eisenman, we did prove that a few years ago, that when you look at Ising in 4D, you get a trivial limit. I mean, what we call a Gaussian limit, which translates into a trivial limit from the point of view of physics. So I'm very much interested in 4D, because then the question is, okay, if you take the Ising model, it's, in some sense, it's not sufficiently subtle to create interaction, like to have a quantum field theory which is rigorously defined, but with interaction. So then, if you want to create interaction, one of the things you can do is go to these gauge models. And the gauge model, in many ways, resemble the Ising model. A lot of what happens is that very often in the Ising model, you look at connectivity properties. In gauge models, you are going to rather look at property of surfaces, basically. And, but some of the tools are similar. It's just that some of the tools break down. And one of the activity in our field is to try to salvage something out of the tools that remain, because there are very deep analogies between these models and the Ising model, for instance. But still, we are very far from doing the dream thing, which would be defining a discrete version of Yang-Mills field and try to take the limits. So try to look at the large-scale behavior and prove in this case that you have a mass gap. So you will not be in a case of a critical behavior, but in a case that resembles more what happens in these things if you draw the analogy with what we do. So this is really something that probabilists in particular attack from different angles. SPDs, if you do things in the continuum directly, or discrete model and trying to take the limit if you are more in my field. So I'm a slow learner, so I do things step by step. So for instance, the first thing I'm trying to do after Ising is to actually try to have spins that are not valued in two directions only, but already like pointing in any direction, because there are challenges, but the analogies are already stronger with what we do. And then the next step would be Yang-Mills, but it will be probably for my students, not for me. I mean, I hope, yeah, but that's a very good question.
Okay, other questions? Yes, well.
Yes.
Thank you for a wonderful talk. I mean, I'm curious because of kind of the lattice that you have, and it seemed throughout your talk, except when you mentioned translation invariance and so forth, that there seems to be a lot of symmetry underlying here. And it's not clear to me what the role of that is. I don't know if there is or not.
So here it's going to be basically translation invariance, except that for technical reason, in order to prove this equality here, we need what we call reflection positivity, which is something very natural from the point of view of physics, because it's coming from exactly the dictionary between quantum and Euclidean that gives you this natural assumption. And this assumption breaks if you take lattices that are less symmetric. But I don't think that it's a mathematically, that it's a physically relevant problem. It's just a mathematical technical problem which we don't know how to overcome for now. So this is there. It's definitely where you will use symmetry more. Planarity for integrability, clearly. And but just to mention about these symmetries, from the point of view of statistical physics, one of the cool questions is to prove that when you look exactly at the critical point of your system, in fact, you expect many other symmetries to emerge. So the large-scale behavior of, say, spin-spin correlation at the critical point, for instance. Of course, if you are on Z2, you have the pi/2 rotation symmetry. But in fact, you expect in the long-range behavior to have a full rotation invariance. And this is another part of my research, is to prove these symmetries, which for Ising were proved by Dimir Chelkak and Stas Smirnov. They prove in 2D that you have conformal symmetry even, so something much stronger. But finding, for instance, in 3D or in 4D, we managed now to prove rotation invariance, for instance. And this is a very interesting question. So anyway, my point is, anyway, the symmetries of the lattice, you expect that they will be enhanced by a lot more symmetries when you look at large-scale behavior.
Okay, so are there any other questions, comments? Please.
So you drew, thank you for your wonderful talk.
Oh, thank you.
You drew the diagrams there for the p equal to 0.499.
Yeah.
P equal to 0.5.
Yeah.
What does it look like if exactly p equals 1.5?
Aha. That's a good question. Let's try to... who think that there is an infinite connected component? I'm just showing you the way. I'm not... Okay, who thinks there is no infinite connected component? Wow, you understood that this is one or the other, right? I'm very confused that in this room this was not clear out of the questions, but yeah, so I see... Sorry? You? The one on the left, so no infinite connected component. But notice, if this is like that, there is something funny about percolation, is that you can easily define a dual model, right? Which is just to say that on the dual lattice, every edge which was white, you make it green for the dual, and vice versa. So here, this picture looks like there is a huge connected of yellow, which is exactly the dual picture of this, and that makes sense because every edge here is open with probability 0.501, okay? So indeed, at 0.5, what happens is that there is going to be a balance, right? Both the red and the green behave, the yellow, sorry, behave the same, and none of them manages to overcome the other one. So what will happen is that you will have a picture that looks like that, where you will have clusters which are all finite, but in a nested fashion. And there becomes exactly related to what you ask. And actually, it's not exactly what you asked, but what I use as a decoy to say what I wanted to say, which is that you have much more symmetries. I just used symmetry. That was much more symmetries there. So in particular, using these symmetries, you can try to describe the interface between these yellow and red edges, and you end up with these fractal curves with like super cool dimension, etc. So here the house of dimension would be 7/4 for this picture, for instance. So there is a whole body of work, I mean a whole field, subfield of statistical physics devoted to understanding this type of behavior. By the way, the main open question in probability theory, so at the critical point, you don't have an infinite connected component. This is basically the drawing idea. It's a theorem. It's not that easy, but you do not have. In Z3, you can ask the same question. Take a three-dimensional lattice, make edges open, I mean red with probability P, white with probability 1 minus P. There is a critical parameter, which is not 0.5, right? It's smaller, clearly, because it's smaller. Prove that at the critical point, you do not have an infinite connected component. It's the main open question in percolation theory. We proved it for this yellow measure, according to that, where it's dependent, but when you have independence, which should be your friend, right? You do not know how to prove the thing. For the people who want. And this I recommend as a career advice.
Okay, so I think we'll finish here. Thank you.
Thank you very much. Thank you.